Hi, this is lesson 4 on plate movement theory. So this is in the specification. It's something that you must be able to do. It's in its own right. You have to talk about why the Earth's crust, which is divided up into slabs or plates, why they move. A lot of this is based still on the theory that you may well have learnt at Key Stage 3 and Key Stage 4, the convection cycle or the convection currents. But also you have additional theory as well, which is called seafloor spreading, ridge push / gravitational slide, and slab pull. And that's alluded to on this diagram. If you hold the video, you'll be able to see some of these things here in operation. Okay, and again, just to reaffirm this, I'll show you where on the spec this is applied to. So if we look here, I've established plate tectonics with you. With the Earth's structure and so forth. We've indicated that the plates move. There are three main basic movements: convergence, divergence, and conservative movement, where convergence where the plates come together, divergence where the plates move apart, and essentially conservative is where they slide past each other. Okay, now the mechanisms in the mantle and the lithosphere, you can see here, I've already talked about those things there. So we need to make sure that you are comfortable with that. After this, then you have that theory where you can talk about it in a 4-mark response, a 9-mark response, and a 20-mark response. So it might be something that is backing up some theory, assessing a theory, but also you'd use part of it in explaining some of the landforms, landscapes that you get created that are talked about here. So just a reminder of, say, what you've learned in the past. The lithosphere is broken up into giant sections called plates. Where they meet are plate boundaries. The theory on this, the plate structures and things like that, really consolidated, I would say, in the late 60s, early 70s, right? So there's, a lot of stuff has been sort of thought about going back hundreds of years, but really coming together with technology, science, almost it's really kind of the accepted thoughts on the structure of the Earth and what's taking place. And again, just to repeat, a bit confusing to look at with all the color coding. Here, the grey line represents the plate boundary, the Eurasian plate, giant slab of Earth's crust, lithosphere there, and you can see it extends over here. And there are several of these, and then there's some smaller ones as well. So this map certainly doesn't show all the smaller ones because it does get confusing, too busy. And on this one, again, you've got this obviously the same plates and the boundaries, but you can see some of the lines of movement. So you can see divergence there. If we look closely there, the arrow is not particularly well represented here. This plate is moving in that direction. That plate is moving in that direction. Something that's not shown on here is that this Pacific plate is moving in that direction, but so is the North American plate. So they're both sliding in the same direction, but at different speeds. You're not expected to learn statistics like this, but again, you can see the slow yearly movement, but how there is a differential across the world. I think, what is it, 8.55? That a quick glance is probably that one moves the most, and you can see in some instances it's not much at all. Plate tectonics has this incredibly slow movement aspect to it, but where you get stored energy, compression and stretching, and then sudden events with large scale movements. So it kind of both ends of the spectrum there. So the forefather, or certainly regarded as the forefather, there's a gentleman called Alfred Wegener from the early 20th century. He came up with this theory of continental drift based on lots of bits of evidence. Very descriptive. The mechanism behind at the time wasn't particularly well explained, understood, and he certainly wasn't the only person that recognized this, but this is one that we allude to. So you've got two elements on this diagram here. You have if we look over here, this is the suggestion, strong evidence to support that 220, 250 million years ago, all the continents that you recognize today were bunched together as one giant supercontinent. And as we go, you can see 200 million years, 135, going through to the present day. They've pulled apart, and they've gone into the position that you can see. And the hyper speed animation here kind of indicates some of that. It's more symbolic than that. Probably helpful. Certainly, the speed of that is way, 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 way too fast. There's papers, research. Scientists say that 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 all the continents will come back together again at some point in the future. I think they call it Pangea Ultima, Ultima Pangea, something like that, where we'll have it again, it all coalesce again, creating huge amounts of volcanic eruptions and earthquakes and so forth. Not something that we'd ever well consider for another couple 100 million years ago. Anyway, let's move on. So let's go to the basic theory first of all. And that's one of the convection cell, which leads into seafloor spreading. I mean, at the end of the day, they're all related, and none of the theories here contradict each other. So bits of the theory that don't explain certain landforms can be added to later on. And certainly the additional theories here, kind of, they're additions. So they definitely work in tandem. There's no contradiction. So if I start by just looking at this picture here, it's a static picture. This is the convection cell theory, the conveyor belt, the convection conveyor belt sort of theory that you learn about in lower down the years, certainly at GCSE. I would say the additional theories are now starting to get taught at GCSE, but you definitely need to know them all for A level. Okay, so if we look here, there's our lithosphere. This plate is moving in that direction. That plate is moving in that direction because of the movement of the magma underneath the crust. Okay, and I'll explain that a little bit more later on. Personally, I would be able to draw this within 30 seconds. I don't mean this work of art. I mean like a 2D picture with very basic labels. It's a great way of remembering things if you can regurgitate these things from memory retrieval in your diagrams with very scruffy labels. On the next couple of slides, we'll put this into more of an animation so you can see the movement of this. So this circular bit here is the movement of magma. Now, in reality, things are always more complicated than what the pictures do. So we're saying magma is rotating around, and we'll explain why. And we'll also go on to explain why these plates are moving, not just because of this, but also because of the seafloor spreading and ridge push and slab pull. So what looks like cloud here in this repeat visual here is meant to be representing the magma. So what we're saying here is, and the time scale of this is nowhere near like this. So there's the outer core, and as the magma, all of it's incredibly hot, by the way, but as the magma passes the outer core, it gets heated up more and more, right? It's going from hot to very hot. And it gets to a point by the time it gets over here, it's now so hot, its molecules are further apart, it's buoyant, it upwells, it goes up. Right now, when it gets here, can you see this angle here? There's this ridge that's formed where this white bit here is, and you can just about make out the gap there. When the magma gets high up here, it's now cool enough to form crust. Now, that crust has to go somewhere, so it pushes the older crust in these directions to make room for it. That's the seafloor spreading. Again, you'll see some more slides on that. And then, so that's the first aid there, and this conveyor belt begins, but it's got that extra shunt there, movement there. The majority of the magma can't form up there and gets pushed to either side. I call it a deflection. And that's because there's this upwelling of magma. And as it moves under this lithosphere, it pushes and drags it along like a conveyor belt, a bit like when you're going to the airport and you're going to the gate at the terminal. By the time we get to this side of the diagram, it's now denser because it's cooled relatively, and then descends. It's also because it's hit another plate here, it gets deflected downwards. And then it obviously dives deep down into the mantle, and the idea is that it's a repeat cyclical process. I've got another just very quick video clip to show this. I'm not going to repeat the same explanation here, but you get the gist of it. And you can see that picture is much more simplistic. Now, moving on to the next picture. I think this is useful. Notice how I've labelled it 5 points, 5 steps. So I could, I don't need to do a color picture. I could do something very simplistic of this, repeat it from memory, have the 5 steps on there, put the labels on there, and then each of those points acts as a trigger to remind me what I need to be able to explain in an answer. So imagine if you've got a 4-mark question that says, explain the convection cycle concept in plate movement, 4 marks, right? This would allow you to do it. So I'll move on to the next slide and read out those. It's a bit of a repeat of what I said before, but done in very, very clear steps. Okay. So step 1, if you can just try to visualize that. Step 1 is the magma is heated at the outer core. Step 2, that's the bit where it's rising up. That's because it's hotter and lighter. That's the upwelling. Step 3 is now under the crust. The majority of it gets moved to either side of it, but some continues to move up where there's a gap, cools, solidifies, and forms new crust. I've also said, like, I haven't talked about the mount. I'm not going to go into the mountains and the volcanoes because I'm concentrating on the convection cell bit here. The majority of the magma that was deflected pushes and pulls it along, and then eventually, far enough away, it's now cooled and become denser and sinks back down to the outer core where that cycle is repeated, and that's known as the convection cell stroke current. Now, we don't need to go into masses of detail. I've already talked a little bit about this first bit, sea floor spreading. So again, it's very distinct in the spec. So we need to make sure that you've got that clear in your head. And we'll go through this and this. Now, towards the end of this video, certainly on the PowerPoint, there's some very, very detailed notes. So if you want to do some additional reading, by all means, go through that. But this video, my talking bit will just be concentrating on getting the basics right. Okay, but there's that extension work. I'll show you that before the end of this video. So just to repeat, so sea floor spreading, all of this works in conjunction. You can see the convection cell coming up, and as we go up here, we get to this point here, and it's cool enough to start solidifying, forming weak oceanic crust, and it pushes the older crust in this direction. If you date the rock, as you go there, you find it gets older and older. A really good way of doing that is paleomagnetism, right? So the rock gets older. So it's creating new crust and it pushes the older crust that way. So you can see there's this additional push force, okay? Now, the other thing that we need to really get across here is this idea of ridge push, stroke, forward stroke, gravitational sliding. Now, if we look closely here, you can see this is a high point. There would be ocean above that, so it's not quite to scale this diagram. And notice it's pointing up. That is a mid-ocean ridge. Now, the one in the Atlantic is about 2 to 3 kilometers tall and still has ocean above it. And the reason for that is that you don't get crust forming down here because it's too hot, and it's only cool enough here to form rock, but also once it starts forming there, you can see how that shape allows the magma to get up there as well. Now, the relevance of it, if you go to the top point, if I just move the mouse out of the way, that's where the crust is being formed, and it's forming at a high point. And therefore, when it does move, it's going from the top of the ridge. So it's got that extra shunt because it's a high point. If you think when you go on a slide, why do you go down on the slide? Because you're aided by gravity. So you've got extra crust with the sea floor spreading, but the ridge push is that extra shunt it gets there because of gravity. And it's like sliding down there. So it's like that angle assists the movement. And I say, a lot of scientists say the convection cell theory here, they don't think is strong enough to account for all the movement. Still think it's relevant, but they're thinking forces like this. So the extra thrust, but also the angle with the ridge push, gravitational slide. Okay. Now, if you notice on this particular diagram, the lithosphere is getting thicker. It's because of the cooling and the density. If it's getting denser and thicker and denser, when it comes into contact with this plate over here, it deflects downwards, as the word that we'll be using a lot later on, subducts. Okay, so what's happening here is that as it hits here, it goes, tips downwards, okay, because it's heavier, but also we get slab pull. And I'll demonstrate that more on the next slide here. So this crust, as it goes into the mantle, is pulling the plate. So we are pushing over here, convection cell over here, and we have the pulling of the plate into the mantle. So I demonstrate this in class. It's a nice, exciting demonstration. But what we're saying here is I often get like a chain with the plug. Students watch around it, looking sensibly bored. And then what I do is just nudge the plug to the edge of the table. The plug goes over, like you can see with the chain here, and then it pulls the chain after it on its way downwards due to gravity. So as I said, you've got that extra yanking down of the plate. Now, depending on the plate boundary and various different scientists, some people say slab pull plays more of a dominant role. Some people say ridge push plays a role. You're not going to get that type of question in the exam, but you do need to think, right, at the end of this, I can explain the convection cell, I can explain the formation of new seafloor, why that causes spreading. That then leads on to ridge push, gravitational sliding, and then I can understand how the slab or the crust, as it tips into the mantle, we get that slab pull going down. Now, on the remaining slides here, all I've got is repeating some of the information that I've been talking about, but more specifics. So I won't really talk on this bit, just point out a few things. So you can see there's just a little bit more specific information there on seafloor spreading. And there's two slides here on ridge push, gravitational slide, and slab pull, and they've got more specifics. And again here. So these are the fundamentals. As I said, you could get asked direct questions on this. Where I'm going to push on after this, as I'm now in the next lesson, I'm going to start looking at the different plate boundaries. At GCSE, you often learn there are three: constructive, destructive, and conservative. But they each have their subdivisions which you need to be aware of. That's for the next lesson. Thank you very much for listening. See you next time.